Cubic splines, from intuition to construction.
Suppose we want to approximate a smooth function. Instead of fitting a single global polynomial, we divide the domain into smaller pieces. Local models are more stable and avoid large oscillations. Here are 3 scattered data points. A linear fit is simple, but not smooth. A quadratic fit is smoother, yet still not flexible enough. Cubic splines pass through all points while ensuring smooth curvature.
At each interior node, adjacent cubic pieces must meet smoothly. Their first derivatives must match, and their second derivatives must also match.
Now, let's count the unknowns. We have several cubic pieces, one for each interval between the data points. Each cubic has 4 coefficients, A, B, C, and D. So with n data points, we have n-1 cubic pieces. That means 4 times n-1 unknowns in total. But from interpolation and smoothness conditions, we only get 4n-6 equations. So we are missing 2 more equations.
These 2 extra equations come from boundary conditions. Natural splines set the second derivative to 0 at both ends. Clamped splines match the slope at the endpoints. Not splines match third derivatives at the first interior points. Remember our example of the range function? With equidistant points, the global polynomial shot up and oscillated out of control. Let's see what happens if we try cubic splines on the same points instead.
Each segment bends gently between its 2 neighbors. No wild swings, no endpoint blowup. This is the power of cubic splines.
Cubic splines avoid the instability of high-degree polynomials by using many small local pieces instead of a single global curve. Mathematically, for strictly increasing nodes, there always exists a unique natural cubic spline. The system that determines it is tridiagonal and well-conditioned, so even if we add more points, small data errors stay small. There is also a deeper reason for their stability. Among all twice differentiable functions passing through the same data points, the natural cubic spline is the one that minimizes bending energy, the integral of the second squared derivative. This makes it the smoothest possible curve that still fits the data. Thanks to this energy-minimizing property, splines suppress high-frequency oscillations. They don't whip wildly like global polynomials when more points are added. Finally, they come with sharp error bounds. If the data comes from a smooth function, the error shrinks proportional to the 4th power of the mesh size. This guarantees that splines converge quickly and remain stable as we refine the grid.
And that's how cubic splines are built, piece by piece. Subscribe for more math visuals.